All right, so now let's talk about generalizing the notion of affine connections to nonlinear manifolds. Okay, and of course, one way to do this is to introduce a coordinate chart. So let's go ahead and do this. Right, so on a n-dimensional manifold, M, right? Consider a coordinate chart. Okay, with some open set U and some coordinate map phi. Okay, and so the idea is in some sense quite straightforward. You have a manifold M, you have an open set U, you have a map by this to some open set in Rn. Okay, and so what you need, right, is a basis for the tangent space. 2M, it's like with a base point in U, okay? And we've seen this time and again. The way essentially you do this is that on Rn, of course, you have the standard coordinate lines associated with the Euclidean structure. So you can have coordinate lines here, and of course you can pull them back, it's like to the manifold, and that gives you coordinate lines on the chart. Well, technically it only sort of extend up to the domain of definition, it's like of the coordinate chart. So let's just erase that. Okay. And then once you have these lines, of course you can look at the tangent spaces or the tangent vectors to that, and that will give you then a basis for the tangent space at every point it's like in U. Okay, so let's try to do this a little bit more formally. Okay, so the canonical vectors or the canonical basis vector sort of EI, right, is replaced with the ith coordinate vector field. Let's call it big EI, okay, of this coordinate chart, okay. Oftentimes it's like this is denoted in the following way: xi. Okay. So, and that has to do with the fact that one way of thinking about vectors is as a directional derivatives or derivations, right? And then this is sort of the notation associated with that. Okay. So let me try to maybe make it a little bit more precise. It's like what I mean by this ith coordinate vector field, right? Okay. So first you consider a curve. Which goes through the point, let's say y, it's like which is in the domain of definition, it's like of the coordinate chart, okay, y and u, all right, and what you do is you have a map t to the following, okay, so you want to have a line, okay, so let's say this point is y, right, you want to have a line along the ith coordinate chart here, right, which corresponds to that. So what you do, of course, is you take this point y, you look at its image, it's like under the coordinate map. Okay, now this is in Rn. I can add t times e sub I, right? So this is the sort of now a curve, it's like which goes through the image, it's like of y under the coordinate map at time t equals to 0, and then sort of goes in the ei direction as t varies. And then I want to pull that back, it's like to the manifold, so I take the inverse of the coordinate map. Okay, so that's sort of the obvious curve to look at, right? Okay, and then once you have that curve, you can look at the tangent to that, right, or the equivalence class associated with that curve. Okay, so so in particular, what that means is that so if one has a real valued function f, right, on U, right? So of course one way to think about vectors is how it acts on scalar valued functions, right? Then you can check that EI acting on F, right? It's just the obvious thing. It's the partial derivative in the ith component of F composed with the coordinate map, or the inverse coordinate map. So F is a map from U to Rn, right? Sorry, U to R, right? And this is a map from, okay, the coordinate map is a map from U to Rn. And you can ask what this map from Rn to Rn is, right? And of course, it's just the inverse of the coordinate map composed with F, right? Which is exactly this expression here. So this is the local representative, it's like of F, sometimes referred to as F hat, right? And then that is a map from Rn to R. Okay, then I can take the usual derivative in the ith component, and then that's what this thing is. Okay. All right, so the other consequence of this is that the linearization of the coordinate map at some point y in the direction ei at y is just going to be ei. Okay, so that's another consequence of that. So sometimes I will write this as, with a slight abuse of notation, as partial I of F. Okay. All right, where essentially we're sort of abusing the notation by thinking of EI, big EI, as being essentially like little EI. Okay. So in any case, once you have then a basis for the tangent space at every point in U, right, we can expand obviously any vector, it's like with respect to this vector field EI pointwise. Okay. So now, as was the case with the linear expansions, right, we can expand all the vectors, all the vector fields, it's like with respect to this set of basis vector fields, if you will, defined locally, it's like on the coordinate chart. Linear manifolds, right, we can expand some vector field C as the sum over J of Cj, Cj, Ej, and you can do the same thing as before, right? So as before, it's like when you write this sort of arbitrary action, it's like of the nabla affine connection, it's like with this pair of coordinates, right? I can write it in terms of this expansion. Now with respect to this I-th coordinate vector field, big EI, right? Okay, and as before, it's like use the sort of the FM linearity. It's like in the first slot, right, to take the sum out. Then what you do is that you use our linearity to break this up. Maybe I will break it up into 2 steps just to be crystal clear what is going on. Okay, so this is sort of FM linearity in the first variable, right? Then going from here to here, is just our linearity. The second slot. Okay. And then you want to take this out, right? You can't really do that. Okay, so you have to use, this is of course a function now, right? So, but we don't have FM linearity, it's like in this, okay? So we have to use the Leibnitz rule. Okay, in order to get this. Now sum over ij. So that's basically what's happening, right? So, and that's because you can do our linearity from here to here because this sum here is, it just has sort of coefficients 1, if you will, right, in these terms, and 1 is a constant function, so you just need our linearity there. Okay, so anyway, so that's what you do as before, right? This is exactly the same calculation we had done. It's like in the case of linear manifolds, it's like in affine connections. Except that, of course, the expansion was done with respect to just the canonical basis on Rn. Now it's done for respect to this I-th coordinate vector field, which is predicated, it's like on you having a chart that's like in this neighborhood U on the manifold. Okay? All right, so as before, right, you know, the affine connection, then it's like on a coordinate chart is sort of specified. It's like once you've specified these n-squared vector fields, right? So the affine connection is uniquely specified, so fully specified. Once we have selected the n-squared vector fields, right, nabla ei ej. Okay, and then as before, it's like you use the Christoffel symbols, right, to write this as gamma ijk ek. Okay, so I'm going to, that's a vector. I'm going to expand that vector. It's like with respect to this sort of basis. It's like at every tangent space, right, which comes from this I-th coordinate vector field. Okay, and yeah, so I should say there's a sum over k here, right? Again, normally it's like you oftentimes see that because there's a raised k and lower k here, which is matched, right? Oftentimes people will omit the sum, and have this implicit summation over k through what is called the Einstein summation convention. Okay, all right. So with that in mind, it's like what I can do is I can write this, that this output of the connection is given by a sum over now I, j, and k, right, of the following: gamma I, j, k, e, k. Okay. All right, so all I've done here is I substituted this equation here into this expression and then taken the sum out. Okay. All right. And then I can re-index the second piece here, and then re-indexing gives me the following. So re-indexing second term. So the reason I might want to reindex the second term is because I might want I want this to be an ek here, right? Or whatever you prefer. You want this to be the same, okay, in the bottom line. So I can write this as follows. And actually I want that to be, that index to be I, okay. So this is going to be the sum over I, j, and k. Okay. So, right, so I can write this in matrix form, right? So I can write this in matrix form. Okay. That and in terms of hat quantities, which denote the column vector of components in the chart. Components of the vector, right? That's what I mean. Okay, so of course if you have an arbitrary vector, it's like in the tangent space, and you have a chart, right, that induces, you know, it's like these I-th coordinate vector fields, which then allow you to write any vector now as an n-tuple of numbers. It's like corresponding to the coefficients which show up in the expansion in that basis. Okay, so that's basically what I'm doing. I'm going to write this now. It's like as a sort of column vector. Okay, and then this is going to be some matrix having to do with the Christoffel symbols, right? and then let me say something about that matrix. So this denotes a matrix whose ij entries sort of is the real valued function. Okay, given by the sum over k of. So you'll see that this C dependence is in the matrix itself, right? So I'm going to combine, this is the matrix which I'm going to work with, right? That's basically what's happening. Okay, and then I have this sum over this, right? So this isn't a matrix, it's a tensor, right? So it's a multilinear object which acts on 3 indices, if you will, right? So when you contract, it's like by a vector, right? The k, there's an up, and down, there's a sum over it. That sort of gets rid of that k index, and you only left with an ij index, right? So that's basically what's happening. If you contract out, it's like this k index, you only left with ij. So that's exactly what happens. So this is why you can think of this as a honest to goodness matrix now, which is a bilinear operator in some sense, right? Okay, anyway, and then you have to evaluate this at x, right? Okay, so anyway, so if you have that coordinate representation now, then you can conclude the following properties of this affine connection. Okay, so let me erase this. Properties of the affine connection. Right, the first one is the dependence on eta. So the vector field nabla eta c, right, at the point x depends only on the value of eta x, the value eta x of eta at the point x. Right, and that sort of isn't too surprising, right? Because if you recall, the properties of the affine connection are that it is fm linear, it's like in eta, right? So more or less that has to mean that you only have to be able to evaluate that vector field pointwise at a particular point, right? Whereas the affine connection is only R linear in the second slot, so that's where you expect it to depend on more than just the single pointwise value on C. Okay, the second thing is local dependence. Right, on C, right? So in contrast, just a pointwise value, it's like a C is not enough. You need to have more information. And the basic idea, another way to sort of think about this is that if you only needed to know, if all that was necessary was to know the pointwise value of c, then it wouldn't just be R linear in that variable, it would be FM linear in that variable, okay, which it's not, okay. So again, these two observations are consistent, if you will, with the kind of properties which we sort of prescribe. It's like for the affine connection. Okay, does not provide enough information about the vector field. C to compute nabla eta c at x. Okay. But if two vector fields agree on sort of an open neighborhood, of the point x, then these two will agree at x. There's also an additional thing, which is that sort of given furthermore, given two different connections, nabla and nabla tilde, right? The difference of them depend only on the value of c at x. Okay. Excuse me. And the reason for this is because if you look at the expression we had before, right, let me just write this in the sort of the abstract notation, right? Okay, the part which is problematic, if you will, is this term here, right? So this term, right, is exactly what causes you to have a dependence, a local dependence on c, and not just a pointwise dependence on c. But when you take the difference of two affine connections, right, so two directional derivatives that's like generated by these affine connections, then that term vanishes. Right, so if you will, it's like you take this difference, right, then you get the sum over ijk, and then gamma jki minus gamma jki tilde, right, and then this term vanishes, it cancels out. And then now it's like you have something which only depends pointwise. It's like on the vector field. Okay, so that's sort of another way to see it. Is that the part which gives you a problem is this term, so this is the term which is responsible for you not just having pointwise dependence on C, but local dependence. All right. But when you take the difference of two of these covariant derivatives, right, then that term vanishes, and you're just left with these terms, which then can just be interpreted in a pointwise way. Okay, so that's sort of a second observation. And then finally, you can check that there's a uniqueness theorem. So the uniqueness of zeros. Okay. So let's say we have two affine connections. On M, and let C and eta and nu, sorry, be vector fields. On M. Then a corollary of this the previous property is that the zeros, it's like agree, irrespective of your choice of affine connection. Okay. Okay, so these two agree with each other if the pointwise value, it's like at 0, is the same. Oh, sorry, the pointwise value at x is 0. Okay, so this property is important. So yeah, of course, this is a consequence of this, right? In the convergence analysis, of optimization algorithms, around critical points of the cost function, right? Okay, so yeah, all right. So that's all we really need. It's like from this notion of a general affine connection. Then the next thing we'll discuss is that, of course, you know, throughout this discussion, we've been talking about not just manifolds, but manifolds endowed, it's like with a Riemannian metric, because, of course, we need to be able to define notions like the gradient. Okay, so the next obvious question then to ask is there some sense in which there is a particular distinguished choice of an affine connection which is associated with the Riemannian metric? Okay, and so that's what we'll be talking about next. So I'll stop here for now.